Okay, class, welcome to lecture 18. Um, so today we're going to talk about the product of sets. So the product of sets is something you've actually used before without saying what it was, and it's sort of like the product of numbers. Last time we sort of tried to make the intersection seem like the product of like a multiplication type thing of sets, but it's not really like that. This one sort of is more, but still not exactly the same as how you multiply numbers. We don't get all the same rules, but we get some similarities. So, okay, let's see it. The idea behind why we might consider these things is really because we want to think about ordered pairs. They're a very useful thing. So what are they? Well, they're just pairs of numbers that you put in a parentheses, like 5, 3, or -1, 2, or you can just have letters or anything else. These are ordered pairs, but we want to think about them in terms of set theory. So we got to do some extra fancy stuff to make it work. Okay, so what we're going to do is we are going to define something. It's a new way to combine two sets. So if A and B are sets, then this other way to combine them is called their product. So their product, or you can call it the Cartesian product as well, but I don't want to keep saying Cartesian product every time, so I'm just going to say product, Cartesian product. Their product, which we write as A and then a multiplication symbol B, but we don't call it A times B, we call it A cross B. That's one way to say it. So what is this thing? So it's a new set that you get by taking A and B and combining them in some way. So here's where we say what that way is. So what we do is we just create all the possible ordered pairs where the first coordinate can only be things in A, and the second coordinate can only be things in B. So this is the set of all possible coordinates you can combine to get ordered pairs. So A, little a, is going to go through all the possibilities of A, little b is going to go through all the possibilities of B. So you're going to get a whole bunch of points, a whole bunch of ordered pairs when you do that. But see how this works, it's just best to see an example, but that's the actual definition. So for an example, let's take two sets. A equals, this guy will have A, B, and C in it. B will have, how about two numbers, 5 and 10. So let's figure out A cross B. So we can sort of just experiment around a little bit. So what kinds of things are in A cross B? Well, the things, the elements, the kinds of things that are in there, that's what this side says. So it's got to be ordered pairs where the first coordinate in the ordered pair, first thing in the pair, has to come from A, and the second thing has to come from B. Okay, so what is something in A? I guess I should color coordinate. So maybe I'll do green here. So what is something in A? Well, A is in A. And what's something in B? 5 is in B. So that means that the ordered pair A comma 5, sorry, I wanted to do color coordination, but I forgot to. So let's do it like this. Um, why did I say that? 5 is in B. 5 is something in B. So since A is in A and 5 is in B, A comma 5 is something in A cross B. So we're listing elements, so that means we put commas between the elements. So it's a bit weird because this whole thing is just one element of the set. Whereas before, we were writing an element, comma another element, comma another element, and each element was always just like sort of one thing. Whereas now each element is actually a pair of things. But then I still separate with a comma. Separate from the next element with a comma still. So this first comma is separating the ordered pair, the second comma, the super comma, separating one element from the next. Okay, so what's another element in here? Well, A can be paired with 10 instead. And that's because the set A cross B is a set of all ordered pairs that you can make by taking something from A and taking something from B. So I can take A from A again, but now I can take 10 instead and also pair it with A. So those are the only elements I can get by using A first, right? Because I've already paired A with 5 and I paired A with 10, so that's all I can be paired with. But now I can look at B, and these ones I won't color coordinate, but same idea. I can pair B with 5 because B is in A, so it can be in the first coordinate. And then I can pair B with 10, and then I could do the same thing with C. I could pair C with 5, and I can pair C with 10. So one thing we should do is just figure out how many elements we have. We have 1, 2, 3, 4, 5, 6. And that's not so surprising because of the word product. So notice A cross B has 6 elements, and A had 3 and B had 2. That's interesting. 3 times 2 is 6. So that's one way in which this product is related to the product of numbers. If you take the number of elements in those two sets you're producting, then the number of elements in the product will be the multiplication of those two numbers. Okay. Let's do another example. So let's use the same B. So 5 comma 10. And let's think about what would B cross B be? So now each ordered pair has, so first I'll write the general definition. Each ordered pair has coordinates which come from the same set. So as I let little a and little b, maybe I'll use different letters. I don't have to say little every time, so I'll just call it x and y instead. So as x and y vary through all the possible elements of B, what elements will I get now when I do B cross B? Well, the first coordinate can be 5, and I can pair that with the second coordinate also being 5. And then the first coordinate can be 5, but I could pair that with 10 being the second coordinate. And then I can make 10 be the first coordinate and 5 be the second coordinate, and then I make 10 be the first and 10 be the second. So now I get this set. And then we can also write this as B squared. So if you cross a set with itself, You can just call it b squared for short. It's a nice notation. Makes sense for products. Okay, so now what else can we do? So let's think about A cross B versus B cross A. And let's use the same. I'll do some new sets just to. This will be, how about X, Y, and 3, and B will be A and 2. Just to confuse you, I put little a in B instead of A. So what I want to do is think about these two sets. Are they the same? Let's find out. So A cross B, what's going to be in here? Well, why don't I write it like this? I'm going to fill out the first coordinates. So the first coordinate has to come from big A, from the set big A. So that means the first coordinate can be X paired with something, it could be Y paired with something, or it can be 3 paired with something. And then it's going to be repeated because I can pair it with multiple things. But anyway, let's just leave it at that for now. Meanwhile, B cross A, the first coordinates for those have to come from big B. So what can the first coordinate be? Now it can only be A or 2. And of course, if you finish it, it's going to repeat. So I guess I'll do that. So X can be paired with A, Y can be paired with A, and 3 can be paired with A. But then I can pair each one of them with 2 instead. Over here to finish that one up. And here, A can be paired with, so now the big A is the second set, so the second coordinates all come from big A, so the second coordinate can be X for A, or it could be X for 2. But then the second coordinate could also be Y for A, and Y for 2, sorry. And then it could also be 3 for A, and 3 for 2. So these sets look very similar. They both have 6 elements in them, but they are not the same set. And we can just think about these two right now. So not the same. So for example, X comma A is different from A comma X. And you can think about this just in terms of ordered pairs that you're used to. So you would never say, like, if you're graphing like 5 comma 3, it's definitely not the same point as 3 comma 5 on the XY plane. So why should this work any differently? They're not the same. And what this means is we have a notion of what does it mean for 2 ordered pairs to be equal. That's what we need to think about it. So we need to say what it means for 2 ordered pairs to be equal. So we can think about what we're really trying to say here. So it's not too tricky. It should just be that they have the same exact coordinates. So A comma B should, and this is more in general now, this is nothing to do with the examples, this is in complete generality. The coordinate A comma B should equal A prime comma B prime. What should this mean? Well, it should just mean that the first coordinates are the same and the second coordinates are the same. Of course, it's prime to indicate a different variable, not prime the derivative. It's just another way to indicate a new variable. Okay, so So this is what it means for two ordered pairs to be equal. So then two products of sets would be equal. Well, these are both sets, so that means that they have to have the same elements, but all of their elements are ordered pairs, so they better have all the same ordered pairs. Now, of course, if you write the elements in a different order, that's okay. They still count as being the same set. So for example, I could say something like this: 1, 3, 2, 5. That is a set with two elements in it, two ordered pairs. That's going to be the same as the set 2, 5 and 1, 3, because all I've done is change the order of the elements, but the elements themselves are the same. Now try to keep up. Well, this one is a little bit different. I'm not reordering the elements. I'm changing the elements. These are completely different sets because the elements themselves are different. One, 3 is not the same as 3, 1, for example. Here, 1, 3, it doesn't need to be equal to 2, 5. They don't have to be in the same order. It just has to equal something on the other side, and it does. And then the 2, 5 also needs to equal something on the other side, and it does. So they have the same exact elements. They don't have to be in the same order. They just have to be the same elements. Okay. So just as a final note, in general, A, B does not have to equal B, A. And A cross B does not have to equal B cross A for the same reason. That's a bit weird because that's definitely different than how products of numbers work, right? 5 times 3 is 3 times 5. But here, they're not the same. They're very related, and we'll probably get to that later, hopefully. But they're not equal. Okay, so let's think of more examples. The XY plane is a wonderful example. So it's actually a product of sets. It's R cross R, which of course we can call R2 now. So why is the XY plane R2, R cross R? Well, let's just write out what this is. R cross R is the set of ordered pairs where the first coordinate comes from a real number and the second coordinate is also a real number. But that's exactly the same as the plane, because the plane is just a bunch of XY coordinates where X coordinate is a real number and Y coordinate is a real number. I just used the letters XY instead of AB, but I could have used the same letters. The point is that this XY coordinate is an element of the set R2 or R cross R. So a point on the plane is a point in R cross R. So that's nice. We can think of something we already know and have used a lot as a set. So what we're going to do next is think about subsets of R cross R or R2. So the idea is then if you draw a picture on the XY plane, you are indicating a subset automatically of R2. So for example, we'll start off with just something that you've seen before. So how about the line y equals x? So the line y equals x is really a set. It's really the set of points x comma y that obey this relationship that y equals x. So for example, 3 comma 3 is on this line because 3 equals 3. But like 2 comma 5 is not on the line because 2 does not equal 5. So a line or any picture is just a whole bunch of points that you just draw as a nice smooth line because you can't draw all the points. So instead of doing that, you just draw a nice smooth line. Okay, so how do I just say this as a set? So it's what set? It's the set of x comma y's, or you use a comma b's, whatever you want, where y equals x, and that's it. I guess I should say that x is a real number. I don't have to say y is because that implies it, since x already is, and they're equal. So this is a set. So because it's a line, you might want to label it like L or something. And we could further say that L is a subset of R2 because all of its points are points in R2. All of its coordinates look like a real number, comma a real number, but restricted by something. That something is that this equation has to be true about those two numbers. Okay, so any function that you've heard or learned about does this same exact thing. So if you think about the function x squared, you might remember it creates this parabola, and the set describing the points on that parabola we can write down as x comma y's, where y is given by x squared, and x is a real number. And again, because it lives on the plane, it's automatically a subset of the plane, aka of R2. So that's just another way to think about things you've already done. Okay, but functions, that's what you learned about for like 20 years. Functions are boring. Well, they're not boring, but they're very restrictive. Yeah, they always, like, the pictures are just, they got to pass the vertical line test. So they're sort of boring pictures. But we don't have to worry about functions anymore. We can do more fancy things. So any picture I draw, in fact, picks out a subset of R2. So let me draw this rectangle. And I'm even going to shade the rectangle to indicate that all the points that I'm trying to say, that the rectangle and the points inside of the rectangle, they're all in some set. And I want to describe the set. I guess I need to indicate where my rectangle is going from and to. So let's do something like that. I don't claim to draw proportionally. Okay, so I can describe this set, or actually it's a subset of R2, as what? Well, let's think about what it would mean to be in this rectangle by just thinking about like one specific point right here. What property dictates what this point is? Well, the idea is that the x-coordinate is restricted between 1 and 3, while the y-coordinate is restricted between 2 and 5. And that's really all there is to being in this set, because any old point you pick will have the same property. Even the ones on the boundary, they'll be equal. So the x-coordinate here will be equal to 3, but the y-coordinate will still be between 2 and 5. So what this tells us is that the points aka the ordered pairs, x comma y, are given by what? Given by, well, we're going to have to use inequalities. So the x-coordinate, you can have any x-coordinate you want as long as it's between 1 and 3, and it could even be 3 and 1. And the y-coordinate can be whatever it wants as long as you stick between 2 and 5. So as long as you fulfill both of these things, so I don't know, pick something, 1.7 comma 2.3. As long as you fulfill both those conditions, which this one does, you will be in the set. So that's just a little mini example. Okay, so now let's write down the set, the subset. And we'll see something interesting. So it's the set of points on the plane. So this time I'll write it like this. Of course, there's many ways to write the same set. So it's the set of points in R2, but not all of them. Otherwise, I would just stop there, and then what would be the point? I would just say R2. So not all of them, but just the ones that do what? The ones where the x-coordinate is trapped between 1 and 3, and the y-coordinate is trapped between 5 and 2. So if you look at all possible xy coordinates that obey these two properties, you'll get this rectangle. And if the property is not obeyed, you'll get points outside of the rectangle. But also, this is the more interesting part, A is the product of two sets. And this will always work for rectangles that you draw. So the way we can think about it is this keyword and was in the definition of product. So I already used the letter A for a set, so I can't use A cross B. So I'll just use X cross Y. So what I claim is that this is the product of some sets. Maybe we don't know what they are yet, but let's just write down the product definition. The product definition has this word and in it as well. And so what you can do, and what a product is doing is saying, tell me what kinds of things the first coordinate can be, and then tell me what kinds of things the second coordinate can be. And that's sort of what we're already doing here. We're saying that the first coordinate is between 1 and 3, and the second coordinate is between 2 and 5. So it sort of matches up. We just got to write it down very carefully. So here it is. Just going to sort of give it away because it's easier to see once you see one example. So I'm just going to try to make it be the product of two sets. So let me just sort of fill in the blank. So the first set is going to tell me the kinds of numbers. So now I'm just talking about regular numbers. Together, it's going to make a pair, but each set individually is just talking about numbers. So the first set just consists of which numbers? Well, it's the numbers that I want the x-coordinate to be allowed to be. So the x-coordinate is only allowed to be between 1 and 3. So that means that I want this set to just consist of those numbers. And over on the second set, I just want my numbers to be between 2 and 5. And I don't have to use a new letter because I'm just talking about a new set. So in fact, I can still use x here. You can make them both y, you can make them both a, whatever you want. But it's still true because all I'm doing is describing the two sets. So now this set is just all the numbers between 2 and 5. And this product is equal to A because the product of sets is just ordered pairs where you take something from the first guy, and I'll even use different letters, something from the second guy, and you squish them together. So now this is saying that A is coming from the first set. So A is just some number between 1 and 3. It's going to look very fancy because it's got lots of sets inside of sets. But this is what's really going on. This is just saying that the first coordinate is between 1 and 3. And it only looks weird because I didn't name the sets. If I just named this big old thing something smaller, it would look nicer. But I'm just writing exactly what it is. And the second coordinate is coming from this other set. So I'm just writing down that set again. And then that's the end of the set description. So here we got a set inside of a set. Okay, so I know it looks a bit complicated, all this stuff going on, but really this is just saying that to build a rectangle, you just have to take the product of two intervals. These are actually called intervals. So an interval you can visualize by drawing a number line, the number line representing the real numbers. And then you can draw, there's a couple different ways, but for example, you say like, here's 1, there's 3. So I'll indicate the interval by doing this filling in thing, and I'm including the endpoints, so I fill in bubbles at the end. So you may have done that a long time ago or something. So what we're saying is that if I take that interval and I product it with this other interval, maybe I'll use colors here. So this other interval will go from 2 to 5. Then I create a rectangle on the XY plane where the X coordinates, because that one came first, goes from 1 to 3, and the Y coordinates go from 2 to 5, because that one came second. And this will work. You can change the intervals and you'll get different rectangles. So this will always work the same way though. Product of two intervals, which are, intervals are just subsets of R. Will give you or create a rectangle, which is a subset of R2. This is another way in which this product of sets is very similar to the multiplication of numbers. You may have learned how to multiply by sort of drawing boxes where you maybe, if I wanted to multiply 2 times 3, I would draw 2 boxes going this way, which is sort of what's happening here. And then I would draw 3 boxes going up. And so it's sort of doing the same thing here. I'm doing 2 times 3. Where's that 2 coming from? It's really because I'm going from 1 to 3. Where's this 3 coming from? It's because I'm going from 2 to 5. So just another little aside of how it's related to multiplication of numbers. Okay, so just to solidify this, let me jump into one more example. So another way to describe an interval is with absolute values. So I could do something like this. So this is the interval from -1 to 1. So maybe I'll draw the visual down here. And I'm including the boundary, the border, the dots at the ends, the 1, -1. And if I product that with another interval, so this is just the set of numbers between -3 and 3. It's much different than union and intersection, so you should also still be thinking about those older things. Union would just be what are all of the points in total that you get when you glue them together. Intersection would be what they have in common. The product is much different. You create a whole new dimension. These are both lines, and then you create a rectangle. So what is this? What's their product going to be? It's going to be a rectangle, which I'll describe as a set after I draw it. And R2, where the x-coordinate goes from -1 to 1, and the y-coordinate goes from -3 to 3. And maybe I can even do something like this. So you can sort of think about it as this guy is being multiplied to this guy, and you're filling in the rectangle or something like that. I have to learn fancier math to really get this down, so we're not going to do that, but I think the colors help a little bit. And then it's filled in because these are not, they're less than or equal to symbols. If you change that to like an equals, it's just going to be the borders. If you change those to equals. And you get different things if you change it to greater than and stuff like that. Then you'll get like the outside of the rectangle instead. So then just to finish it off, this is the set of coordinates where the first coordinate is stuck between -1 and 1. The second coordinate is stuck between -3 and 3. And it's a subset of R2. Okay. Pictures are pretty though. Okay, so speaking of union and intersection, which I just said, the next thing, which is the more proofy stuff, is to figure out how product combines with unions and intersection. So this is all fun and games, and there's more examples in the lecture problems of things like this, but we do have to try to prove things. So that's the next step. Okay, so here's a big old theorem, big old giant theorem. And I think that this lecture is shorter than before. Maybe I've been getting carried away though. We'll find out. Okay, so let A, B, and C be 3 sets. Then a whole bunch of stuff is true. Sorry, it's a colon. Then I'm just going to write down a whole bunch of cool facts that tell us how the product of sets interacts with intersections and unions. So the first question is, how does it work with intersection? Does it like distribute? What is this kind of thing? So you can sort of think about it. What kinds of elements are in here? Before I continue, what kinds of elements are in here? Well, it's a product, right? So it's got something from the first set and something from the second set. I'll use the letter Y because I don't want to use little b, because then it sort of hints that it's in B. But really what it is the first coordinate is in A, and the second coordinate is in the intersection. So that's really what this set looks like. So it's ordered pairs. And then what does it equal? Well, actually, yeah, it distributes nicely. So it becomes A cross B intersect A cross C. So what we're saying is that this set equals A comma, I'll use a different letter, A comma Z. So sorry, no, I'll use, I'm gonna hint at it. So I'll use A comma B, where A is in A and B is in B. It looks like that set intersected with this other set, A comma C, where A is in A and C is in C. So apparently these two sets are equal. I think that's a bit weird. So the first one is saying you got your stuff from A in the first coordinate, and then the second coordinate is just the stuff that's both in B and C. Whereas over here, what you're doing is you're building your coordinates first. You're saying, okay, give me all the A comma B's. Also separately, give me all the A comma C's. Then intersect those, and whatever those have in common should be the same as what I did over here. So it's a bit weird. Okay, there's gonna be a lot of these, so we're not gonna have time to prove them all. But I encourage you to do what I just did for each of these. But I'm just gonna state them all. So yeah, product also distributes over union, very interestingly. So it distributes over both of them. So that's nice. And then this one I have to write down. You might think, why do I have to write this one down? Isn't it just the same as the first one? Because I'm just showing the distributive property again. Well, actually, it's different from the first one. And why is that? It's because if you cross things, and it's different if you change the order. So you should compare the first and the third one, because they're both telling you how to distribute a product, but they're very different because in general, if I take two sets, x cross y, as we said earlier, is not the same as y cross x. So that's why you actually need a separate rule to check to make sure it works the other way, that it distributes in the other direction, which it does. Okay, 4 is just like 2 except backwards. So I can distribute this way instead. And 5 and 6, they're not really new rules. In fact, I hesitated writing them, but I'm going to, caving to the power of the textbook. So this is saying that the product distributes over the relative complement. But the relative complement is just B minus C, but that's really just an intersection. Remember, that's just the first set intersect the second set complement. So of course it distributes because it's really just an intersection. And we already know from the first rule that products distribute over intersections. So this is really the same as rule 1. If you wanted to prove rule 5, you could just use rule 1 to prove it if you've already proven the first rule. So anyway, let me finish writing it down. A cross B minus A cross C. And then 6, same thing, but with the other direction. So if I do A minus B cross C, I can do I can do A cross C minus A cross B. So again, those rules actually come from the other ones. And then these ones are sort of different to tell you how subsets work. So I have to bring in a new set. So I'll just call it T. So if you have a subset of A, then you product both of them, well, it's going to maintain the same status. Meaning, if I product with B, it's still going to be a subset of if I product with A, which hopefully is believable. And if I product on the other side, then it'll be the same. Maintains the subset direction. So I'm only going to prove number 2, but I encourage you to try to prove number 1. And then try to prove number 3. It should be similar to 1, and 4 should be similar to 2, and then 5 and 6 should be similar to 1 and 3. So if you have the time, you should try to prove all these. Okay, So I will prove 2. Proof of 2. Hopefully it'll give you enough of a guide to prove the other ones. Okay, so 2 is we want to show that A cross B union C equals A cross B union A cross C. So we're doing the distributive property, products over unions. So because we're trying to show 2 sets are equal, we're going to do our usual trick of showing that they are subsets of each other by letting an element be in 1. I'm going to call it Z this time because I don't want to use X, and I'll see why in a second. So I'll let Z be in this one and show it's in the other one as a result, right? That's the idea. To show that one is a subset of the other, and then we'll do vice versa. Okay, so now we just say what everything means. So since Z is an element of this set, well, we got to really think about what an element of this set looks like. So I'll just write that down. An element of this set looks like, how about I use X and Y this time? It looks like ordered pairs because it's a product where the first coordinate comes from A, and the second coordinate comes from B union C. So if Z is in there, it's one of those guys. So Z is one of those ordered pairs. So I'll just say that, where X is in A and Y is in this union. And now that's the straightforward part of the proof. The tricky part of the proof is realizing that this tells you that there's cases. So now what we can do is a proof by cases. What happens if Y is in C? Or sorry, what happens if Y is in B? Then what happens if Y is in C? So this creates cases. Case 1, if Y is in B, where can I go from there? Well, what do I know? Then I know X is in A and Y is in B. Well, that means that the ordered pair is in A cross B. That's just definition of ordered pairs. Is that good? Yeah, that's good, because what do I want to show? I want to show that Z, aka my ordered pair, is in a union of 2 things. That just means I need to show it's in one of them. Well, it looks to me like it's in this left one. So great. Well, let's write that down. So thus, Z equals X comma Y, that's what I was looking at, Z is in A cross B, so it's also in A cross B union whatever the heck you want, because it's in one, it doesn't matter if it's in the other at all. So it's in there. It's in their union. That's what I wanted to show. Oh, sorry, that should be a C. Good. So now the other case. It's going to work very symmetrically. So what we were saying was Y is in this union of B and C. So it's got to be in one or the other. If it's in the first, that happens. And now if it's in the second, what happens? Well, it's going to work the same. Then X is in A and Y is in B. So the coordinate is in A cross C. Sorry, I keep changing the letters. Y was in C, that's what I said. Okay, so anyway, the coordinate is in A cross C and everything works exactly the same. So thus, Z, thing I was originally looking at, is in A cross C, but that means it's in this union again because although it's not in the first piece necessarily, it is in the second piece. And that's enough to be in the union, so we're done. This covers all the cases. So what we've shown is this. We've shown the first part of set equality, meaning we've shown a subset proof in one direction. Now we got to show the other direction. So now I'll let Z be in the other guy. Don't have to change the letter because I'm just restarting the proof. It's not the same Z anymore. So now let Z be in there and show it's in the first one, which was A cross B union C. Okay, so how do I get from there to there? Well, I'm just going to think about exactly what it means for Z to be in this set. And so I do have to rewrite lots of stuff when I do that, but that's okay. So I have to write extra stuff. So what is this set exactly? Well, it's a union of two things. So actually, I don't want to write it out because what I want to realize is that since it's a union, it's created two cases for me, and that'll make my life easier. So this is the tricky part of the proof. This creates two cases. Case one, if Z, because it is in the union, it's got to be in one or the other. So if it's in the first one, we'll see what happens, and then if it's in the second one, we'll see what happens too. So let's pretend it's in the first one. Trying to get over here. Okay, sort of see where to go. If it's in there, then that means it looks like an ordered pair where the first guy is in A and the second guy is in B. So I really want that A comma B to live in this thing, this slightly more complicated thing. Well, I already have A living in A, so now I need B living in there to make it work, but B already lives in B, and that's enough to live in A union. So thus, B lives in B union C automatically. Just by virtue of living in one of them, it lives in the union. So A comma B automatically lives in A because little a lives in big A, and B cross B union C because little b lives in B union C. So that's what we wanted to show. And so the first case is done. Case two, if instead of being in A cross B, it's in A cross C, now we got to see what happens there. It's going to work just the same. So now that means that Z looks like a coordinate A comma C. You could reuse the letter B, but I just like to hint at where the element lives by using a smaller, what is it called? A non-capital letter that corresponds to the set. All right, anyway, so Z is an ordered pair A comma C where A lives in A and C lives in C. But then the same as before. So just by virtue of living in C, it automatically lives in the union because it just has to live in one or the other. So the ordered pair lives in A cross B union C because little a lives in big A, so that gets you your first coordinate. And little c, sorry, I changed the letter, lives in B union C, so that gets you the second coordinate. Okay, so this shows exactly what we wanted to show, that A cross B union A cross C is a subset of A cross B union C. So together with the first part of the proof, we've shown that the two sets are actually equal because they are subsets of each other. And so they got to be the same thing. Okay, so I hope that this lecture was shorter than 50 minutes because they keep going up to 50 minutes. All right, so see you next time.